Right now, as you lie here, somewhere far beyond the orbits of all 8 planets, a small spacecraft from the 1970s is still moving outward. Voyager 1, a NASA probe, is now more than 15 billion miles from the Sun. And yet, by many scientific definitions, it still hasn't left the solar system. That simple fact bends the mind a little. Because if a machine has been traveling for nearly half a century at more than 10 miles per second, and it still isn't outside, then what exactly is the edge of the solar system? Is it where the planets end? Is it the moment sunlight becomes too faint to warm anything? Or does the true boundary sit all the way out in the Oort Cloud, a frozen sphere of trillions of icy objects so far away that no spacecraft has ever seen even one of them? Tonight, we're going to follow that question, slowly, gently, step by step. You're lying still, perhaps preparing to sleep, but your mind is about to travel farther than any spacecraft has ever managed. We'll drift past the planets, through the icy frontier beyond Neptune, into the vast shell of the Oort Cloud. And when we finally reach the place where the sun's breath runs out, the heliopause, we'll meet Voyager again, waiting quietly in the darkness of interstellar space. Neil deGrasse Tyson said, "The solar system is far bigger than our instincts ever tell us." So let's begin where everything begins, at the sun. Before planets, before orbits, before anything we now call the solar system, there was only a cloud, a cold, dark nebula, a drifting mixture of hydrogen, dust, and the quiet leftovers of ancient stars. For millions of years, that cloud floated undisturbed, until something, perhaps the shock wave of a distant supernova, stirred it, and the entire region began to collapse inward. As gravity tightened its grip, the cloud's center grew hotter, denser, brighter, until one day, the pressure became so great that atoms of hydrogen fused into helium. A new star ignited, and the sun was born. Tonight, this is where our journey starts, at the heart of everything we know. The sun holds 99.8% of the mass of the entire solar system. Every planet, every moon, every asteroid, all of it combined, is just the leftover dust that failed to become part of the star. It is not an exaggeration to say the sun is the solar system. The planets are simply the ornaments caught in its gravity. Every second, the sun fuses nearly 600 million tons of hydrogen into helium. With each breath of fusion, it releases an immense wave of light and heat in all directions. Some of that light reaches Earth after traveling 8 minutes and 20 seconds, crossing 149 million kilometers of open space just to touch our world with warmth. But the sun does far more than shine. Its gravity holds every planet in orbit. Its wind, a constant stream of charged particles, flows outward at hundreds of kilometers per second, and its magnetic field, tangled and powerful, stretches across billions of miles. Sometimes that magnetic field snaps, solar flares erupt, coronal mass ejections, immense clouds of plasma, surge outward. When these storms hit Earth, they can disturb GPS signals, tug at our power grids, and fill the sky with auroras that shimmer like curtains of light. Yet despite its storms, the sun is astonishingly steady. A gentle star, stable across billions of years. The rare foundation that allowed life to emerge on our small world. But perhaps the most profound thing the sun does is breathe. The solar wind, streaming outward in all directions, creates a vast bubble around the entire solar system, the heliosphere, a shield of charged particles that protects us from much of the radiation drifting between the stars. This bubble extends so far that every planet, even Neptune, sits deep inside it. When you imagine the solar system, it's easy to picture orbits, rings, and planets. But what truly defines it is the reach of this star, its gravity, its light, its winds, and the invisible bubble carved from the darkness. Tonight, we begin our journey from this center point. Let's take our first step to the scorched little world at 0.4 AU, Mercury. Leaving the Sun, the first world we meet is a small, battered sphere only 0.39 AU away, a place so close to the star that every inch of its surface has been shaped by heat and impact. Mercury is the smallest planet in the solar system, yet it carries the oldest scars. Its crust is covered in craters, ridges, and shattered plains, a frozen record of the violence that once filled the early solar system. Unlike Earth, Mercury has no weather, no oceans, no wind to erode its surface. Nothing washes the past away. What you see today is almost exactly what stood here billions of years ago. Because Mercury has almost no atmosphere, it cannot hold heat or block sunlight. And that leads to one of the most extreme temperature swings anywhere in the solar system. In the daytime, when the sun dominates half the sky, the surface can reach nearly 800 degrees Celsius, hot enough to melt tin and lead. But once night falls, with no air to trap the heat, the temperature plunges to 290 degrees, a difference of more than 1,000 degrees between sunrise and midnight. And yet, the strangest thing about Mercury isn't its heat, but its day. Mercury spins very slowly, so slowly that one full rotation takes 59 Earth days. But because it moves quickly around the sun, completing its orbit in just 88 Earth days, a single day from sunrise to sunrise lasts a staggering 176 Earth days. Imagine standing on a world where the sun rises only twice a year, and each sunrise brings a wave of heat that lasts for months. One of Mercury's greatest scars lies near its equator, the Caloris Basin, one of the largest impact structures in the entire solar system. Roughly 960 miles across, it was carved by an object so massive and so fast that the shock waves traveled around the entire planet, leaving ripples on the opposite side. Mercury has no seasons, no weather cycles, no tectonic shifts. Its magnetic field is weak, its exosphere thin as dust. It is a world stripped down to essentials, a planetary skeleton exposed by the sun. Planetary scientists sometimes say Mercury is the skeleton of a planet, stripped to its bones by the sun. And standing here, even in imagination, you understand why. For billions of years, Mercury has remained almost unchanged, a burnt, silent relic sitting on the sun's doorstep. But as extreme as Mercury is, it is only the first lesson in what sunlight can do to a world. From a scorched world, we now move to a world that drowned in its own heat. Venus. As we drift farther from the sun, the second world we meet feels strangely familiar at first glance. Venus sits at 0.7 AU, almost the same distance from the sun as Earth, and nearly the same size. Mass, diameter, density, all close enough that astronomers once called it Earth's twin. But twins don't always grow up alike. The moment you approach Venus, the differences become overwhelming. Its entire planet is wrapped in an atmosphere so dense, so heavy, so reflective that sunlight barely reaches the surface. The air is made mostly of carbon dioxide, with clouds of sulfuric acid swirling above like a permanent toxic storm. Looking at the ground with normal light is almost impossible. Every mission that mapped the surface needed radar just to see through the clouds. And beneath those clouds is one of the most hostile environments in the solar system. The surface temperature hovers around 900 degrees Celsius, 475 degrees Celsius, hotter than Mercury, even though Mercury is closer to the Sun. The crushing air pressure is 90 times that of Earth, equivalent to standing a kilometer under the ocean. If you could stand on Venus, which you can't for long, it would feel like being at the bottom of a deep sea, inside an oven, breathing toxic air. How did a world so similar to Earth become so different? The answer is the runaway greenhouse effect. Venus may once have had shallow oceans, but as the young sun warmed, more water evaporated. And water vapor is a powerful greenhouse gas. It traps heat. That extra heat caused even more water to evaporate. More vapor meant more heating. A feedback loop began. Warm, evaporate, trap heat, warm more. Until eventually the oceans, if they ever existed, boiled away entirely. With the water gone, CO2 dominated the atmosphere, locking the planet into a state of permanent crushing heat. Even time behaves strangely here. Venus rotates so slowly that one full day, sunrise to sunrise, lasts longer than its entire year. And it spins backwards, so the sun rises in the west and sets in the east. The sky, the ground, the air, the calendar, everything is inverted. Could anything live here? On the surface, almost certainly not. But high in the clouds, where temperatures and pressures are milder, some scientists once wondered about drifting microbes. It remains only a hypothesis, with no evidence. But it hints at how strange Venus truly is. NASA once described it simply: Earth's twin in size, but a hell in every other way. And we now move to the only planet we know for certain is alive. Earth awaits. At 1 AU from the Sun, conditions soften. Temperatures ease. Light is warm rather than violent. And in this thin band of space, something extraordinary happened. A planet found balance. Earth is the only world we know where liquid water lies stable on the surface. Not ice, not vapor, but oceans, covering about 70% of the globe. Water is the great solvent of chemistry, the medium that lets molecules meet, react, and assemble into something more. Without it, life, at least as we know it, struggles to begin. With it, life has room to flourish. The air above those oceans is just as rare and necessary. An atmosphere dominated by nitrogen, N2, and oxygen, O2, with just a trace of carbon dioxide and other gases, thin enough to let sunlight through, thick enough to warm the surface gently, trapping heat like a soft blanket. And in the upper layers, a fragile shield of ozone absorbs harmful ultraviolet light long before it reaches the ground. Earth is not only warm, it is protected. A magnetic field, generated by the motion of its molten iron core, reaches far into space. This magnetosphere deflects most of the solar wind that would otherwise strip the atmosphere away. Without it, our air and oceans might have vanished long ago, dispersed into space, as happened on Mars. But Earth's most profound stabilizer is something far more familiar: the Moon. Billions of years ago, according to the leading theory, a Mars-sized object, often called Theia, struck the young Earth. The collision was violent, melting crust and sending vast streams of molten rock into orbit. From that debris, the Moon formed. Since then, The moon has acted as a cosmic anchor, holding Earth's axial tilt steady at roughly 23.5 Richter. Without it, our tilt could wander chaotically over millions of years, flipping between extremes, reshaping climates, turning stable seasons into violent cycles. With the moon, Earth's climate stays within a narrower, more livable range. The moon also pulls at Earth's oceans, creating tides that stir coastlines, drive nutrient cycles, and may have played a role in the rise of early life. Every wave that collapses onto a beach carries the subtle influence of a 4.5 billion year partnership. Earth has not always been peaceful. It has endured meteor impacts, global ice ages, supervolcanoes, and continents tearing themselves apart. And still, somehow, it remains the only known oasis in a silent universe. Carl Sagan once said, "The Earth is the only world known, so far, to harbor life." And when astronauts saw it from the moon, a blue, delicate sphere hanging in darkness, many described a sudden sense of fragility and gratitude. From here, at 1 AU, Earth feels immense, familiar, unshakable. But from a distance, it becomes a pale dot. A small, bright island surrounded by impossible emptiness. Everything you have ever known, every voice, every memory, every story, exists on that thin shell of air wrapped around a rock. And it is the only proven place in the universe where life breathes. Hold that thought gently, because as we leave Earth behind, we step toward colder ground, thinner air, and worlds where life, if it ever existed, had to fight much harder. But just 1.5 times farther from the sun, the story changes again. On a small red world we've dreamed about for decades, Mars. At 1.5 AU from the sun, sunlight softens again, and temperatures drop into a world of thin air and red dust. Mars is smaller than Earth, with only 38% of Earth's gravity, and it feels like a place caught between what it once was and what it has become. Today, Mars is a cold desert. Its sky is tinted butterscotch by fine dust suspended in a whisper-thin atmosphere made mostly of carbon dioxide. Wind lifts that dust into storms that can wrap around the entire planet, storms large enough to darken the surface for weeks. And although Mars has weather, it has almost no protection. Its atmosphere is less than 1% the thickness of Earth's. But the surface tells a completely different story. Ancient river channels snake across the plains, dry, cracked, but unmistakable. You can trace the curves of valleys where water once flowed freely. There are lake beds, sediment fans shaped like deltas, and even long, smooth shorelines etched into the edges of the northern lowlands. Hints that a vast ocean may once have covered the northern hemisphere. Billions of years ago, Mars was warmer. Thicker atmosphere, stable liquid water, clouds, rain. A young world far more Earth-like than the one we see today. So what happened to the water? Part of it is still here. At the poles, ice caps shine bright against the rust-red terrain, and radar data from orbiters show layers of buried ice beneath the surface at mid-latitudes, frozen reservoirs locked away in the soil. But most of Mars's ancient water was likely lost to space. Without a global magnetic field, the solar wind had direct access to the atmosphere, slowly stripping it away over billions of years. As the air thinned, pressure dropped below the level where liquid water can exist. Rivers evaporated, lakes froze. The ocean retreated into ice or vanished altogether. Yet Mars still holds the scars of its more dynamic past. To the west rises Olympus Mons, the largest volcano in the entire solar system, nearly 3 times the height of Everest, its base sprawling wider than the state of Arizona. To the east, the crust splits open into Valles Marineris, a canyon system over 2,500 miles long, deeper and longer than the United States. Seen from orbit, it looks like the planet was torn apart. Despite its silence today, Mars is not empty. Rovers, Spirit, Opportunity, Curiosity, Perseverance have spent years crawling across its plains, drilling into rocks, analyzing ancient sediments, and searching for chemical hints of past microbial life. Their mission is simple, but profound. Look for evidence that Mars once hosted life at the microscopic level. And for the future, both NASA and SpaceX imagine humans standing here someday. Not tomorrow, not soon, but eventually, through slow, careful steps, the way space exploration always unfolds. Mars carries a strange feeling, familiar but distant, friendly in size, hostile in climate, a world that almost made it, almost stayed warm, almost stayed wet. Jim Green from NASA once said, "Mars is the place today where science fiction meets science fact." And he's right. It's where our imagination and our data overlap more than anywhere else. Mars may not be dead. It may just be very quiet. And now, between this red desert and the giant that dominates the outer solar system, lies a region filled with the remnants of planets that never formed. Between Mars and Jupiter is a graveyard of building blocks, the asteroid belt. Between 2.1 and 3.3 AU from the Sun lies one of the most misunderstood regions of the solar system. Movies often show it as a chaotic minefield of tumbling boulders, rocks scraping past each other, ships dodging collisions. But the truth is calmer and far more interesting. The asteroid belt is mostly empty space. If you stood on one asteroid, you would not see another one nearby. Most objects here are separated by hundreds of thousands of miles. A spacecraft passing through the region has a better chance of hitting nothing at all. And that is exactly what has happened every time we've flown through it. So why does this place exist? Why a ring of debris instead of a finished planet? The answer lies in the presence of a giant. In the early solar system, dust and rock clumped together to form worlds. The same process that built Earth, Mars, and the moons of the outer planets. But in this region, the gravity of Jupiter, enormous, persistent, disruptive, prevented the material from sticking together. Every time dust tried to gather into something larger, Jupiter pulled, tugged, and stirred the region apart. The result was not a planet, but the remains of a planet that never formed. Still, the belt contains worlds worth knowing. At its heart lies Ceres, the only dwarf planet in the region. Just under 600 miles wide, it may hide a briny subsurface ocean, a hint that even small bodies can hold surprising complexity. Nearby are Vesta, Pallas, and Hygeia, each shaped by ancient collisions. Some have giant impact basins. Others carry the signatures of volcanic activity from long ago. They are not random rocks. They are pieces of early solar system history, frozen in place. The asteroid belt is also the source of many near-Earth objects. Over time, gravitational nudges send some asteroids inward. A few of them eventually cross Earth's orbit. The impact that ended the age of dinosaurs, the crater at Chicxulub, may have started its long journey from this very region. And yet, the belt is not only a relic of the past, it may someday shape the future. Asteroids contain metals, silicates, and frozen water. Water, once broken into hydrogen and oxygen, becomes rocket fuel. Metals become building material. In the distant future, this quiet ring of debris could help support travel deeper into the solar system. Harold Levison once described it simply: the asteroid belt is the debris of creation. And standing here, in imagination, that feels exactly right. This isn't a danger zone. It's an archive, a museum of unfinished worlds, a record of what almost happened. And just beyond this scattered, silent region, the first true giant of the solar system waits for us. Beyond this unfinished world, the first true giant waits. Jupiter, 5 times farther from the Sun than Earth. At 5 AU, the solar system suddenly widens, and a world unlike any other comes into view. Not a rocky surface, not a place you could stand, but a colossal sphere of gas and storms, so large and so heavy that it could have become a star if it had just a little more mass. Jupiter is 318 times more massive than Earth, a gravitational anchor that pulls on everything around it. In a sense, it is the second architect of the solar system, right behind the Sun. Its upper layers are made of hydrogen and helium, but the deeper you go, the stranger the physics becomes. As pressure climbs to unimaginable levels, hydrogen, the lightest element in the universe, compresses into metallic hydrogen, a form of matter we cannot create naturally on Earth's surface. This metallic layer generates a magnetic field so intense it dwarfs our own, up to 20,000 times stronger than Earth's magnetic field. Wrapped inside that magnetic shield are storms larger than planets. The most iconic is the Great Red Spot, a hurricane-like vortex that has raged for at least 350 years, likely longer. It is wide enough to swallow Earth twice over. Winds here can exceed 270 miles per hour, circling in an endless swirling loop of rust-red clouds. Jupiter's gravity extends far beyond its storms. It tugs on tens of thousands of small bodies, comets, asteroids, icy fragments left from the solar system's formation. Some of those objects Jupiter pulls inward, removing them from dangerous trajectories. Some it absorbs entirely, acting like a cosmic vacuum cleaner. But Jupiter can also sling objects outward or inward, depending on how they pass by. Some ancient impacts on Earth, including the one that ended the dinosaurs' era, may trace their long origin back to this region. Yet Jupiter's most beautiful mysteries orbit just outside its main cloud deck. 4 worlds discovered by Galileo in 1610, each one a complete story of its own. Io, closest to Jupiter, is a world of fire. Its interior is tugged and stretched by Jupiter's gravity, creating heat that fuels hundreds of active volcanoes, more than any other place in the solar system. Lava lakes, sulfur plumes, and molten scars reshape its surface constantly. Europa is the opposite, a smooth shell of ice, bright and clean, with cracks that hint at movement below. Beneath that ice, almost certainly, is a global ocean, possibly containing more water than all of Earth's oceans combined. Dark plumes have been spotted erupting from the surface, hinting at a dynamic, warm world beneath. And where there is water, there is potential. Ganymede is the largest moon in the solar system, even bigger than Mercury. It is the only moon known to have its own magnetic field, suggesting a metallic core and a complex interior. It, too, may harbor a deep subsurface ocean. Callisto, farthest out, is ancient and heavily cratered, a quiet archive of early solar system history. But even this battered world may contain a hidden ocean beneath its ice. Together, these 4 moons form a miniature system: volcanic worlds, icy oceans, magnetic layers, all orbiting a giant that dominates everything around it. George Wetherill once called Jupiter the gatekeeper of the solar system. And it's true. Without Jupiter's mass, Earth might have endured far more devastating impacts over the past 4 billion years. With Jupiter, the solar system has a guardian, imperfect but essential. Standing here in imagination, Jupiter feels like a reminder of scale, a reminder that our solar system isn't just planets arranged in a line, but forces, giants, and oceans hidden beneath ice. And beyond this massive shield, the light from the sun dims, temperatures fall, and the next great world appears, a world famous not for storms, but for beauty. Beyond the giant shield lies the most photogenic world in the solar system, Saturn. At 9 AU from the sun, the solar system grows quiet. Temperatures drop, colors fade, and then, without warning, a world appears that looks less like a planet and more like an artwork. Saturn is a gas giant like Jupiter, but lighter and gentler in appearance. It's the least dense of all the planets. So light, in fact, that if you could place it in a colossal ocean, Saturn would float. A pale golden sphere wrapped in whisper-thin clouds. But it's the rings, the astonishing, impossible rings, that turn Saturn into a palace of ice. The rings stretch more than 170,000 miles from edge to edge, yet they are incredibly thin. In many places, only 10 to 30 meters thick, no taller than a house. They are made of countless pieces of ice and rock, from powdery grains to chunks the size of boulders. Sunlight scatters off these icy fragments and creates the shimmering, layered glow that we see from afar. These rings are divided into bands, some bright, some dark, separated by gaps like the Cassini division, carved slowly over ages by gravitational tugs from Saturn's moons. Even here, in this serene-looking world, everything is shaped by motion. Above Saturn's North Pole sits one of the strangest features in the solar system, a hexagon-shaped storm, a perfect 6-sided jet stream larger than Earth itself. Its cause is still not fully understood, an atmospheric rhythm that refuses to reveal its secrets completely. But the story of Saturn is not just about the planet. It is about the worlds that orbit it. And among those worlds, 2 draw more attention than the rest. Titan, the methane world. Titan is Saturn's largest moon, bigger than Mercury, and it stands apart in a profound way. It has a thick atmosphere, richer than Earth's in pressure, made mostly of nitrogen. Through this golden haze, radar images reveal rivers, lakes, and seas, not of water, but of liquid methane and ethane. Titan has weather, rain, clouds, winds, storms. It has dunes, valleys, and carved coastlines. It is a world with familiar shapes, but alien chemistry. An Earth-like personality expressed in completely different materials. Scientists think Titan may hide a global subsurface ocean as well, sealed beneath its icy crust. A double ocean world. Methane above, water below. Enceladus, the ocean, beneath the ice. Enceladus, a tiny moon only 300 miles across, is one of the most promising places for life in the entire solar system. At its south pole, towering geysers erupt through long fractures in the ice, jets of water vapor that shoot into space like fountains. NASA's Cassini spacecraft flew through these plumes and found salts, organic molecules, and tiny grains that likely came from a warm ocean beneath the surface. Imagine that, a moon so small you could drive across it in a day. Yet beneath its frozen exterior lies an entire ocean kept warm by tidal forces. Carolyn Porco, a key scientist on the Cassini mission, once said, "Enceladus is the place to go if you want to look for life today." And standing at the edge of those geysers, even just in imagination, the statement feels very real. Compared to Jupiter, Saturn is quieter, softer, but no less mysterious. Its beauty draws your eyes, but its moons keep your mind awake. Titan, with its stormy methane seas, Enceladus with its hidden waters, a world where the search for life points not to the surface, but to the depths below ice. Saturn may be the most photogenic world in the solar system, but its greatest secrets may be hidden in the darkness beneath its moons. And now, we leave the Palace of Rings and drift deeper into the cold, toward a tilted pale blue giant waiting far beyond. But now we sail deeper, to the cold tilted giant at 19 AU Uranus. At 19 AU, the sun has dimmed to a pale coin, still bright, but distant enough that warmth feels like a memory. Here, in this quiet region of the solar system, we meet one of its strangest worlds. Uranus is an ice giant, a planet made not of solid ground, but of compressed water, ammonia, and methane beneath a cold atmospheric shell. Its soft blue-green color comes from methane, which absorbs red light and scatters the cooler hues back into space. But its color is not what makes Uranus unusual. It is the way it leans. Unlike any other planet, Uranus is tilted by 98 degrees, essentially lying on its side, as though it once took a glancing blow, powerful enough to topple it. Most planetary scientists believe that in the early days of the solar system, a large body, perhaps even a protoplanet, struck Uranus and left it permanently rotated. This sideways tilt changes everything. At the poles, sunlight can shine continuously for 42 Earth years, followed by 42 years of darkness. Imagine an entire human lifetime where the sun never rises or never sets. Meanwhile, the equator doesn't face the sun directly. It faces outward, toward space, giving Uranus a slow, rolling ball kind of rotation. Despite this unusual geometry, the planet itself appears calm. Its cloud bands are subtle, pale, and often difficult to detect. Yet below that quiet surface, storms do exist, faint, deep, and hidden beneath layers of haze. Uranus has faint, dark rings, far less dramatic than Saturn's, but still structured into several narrow bands. These rings are likely made of carbon-rich material, absorbing sunlight instead of shining. Orbiting the planet are 27 known moons, many named after characters from Shakespeare and Alexander Pope. Some, like Miranda, show cliffs and fractures, suggesting dramatic upheavals in their past. Others appear smoother, more ancient, frozen in time like relics of early solar system history. Uranus is also one of the coldest places in the solar system, with temperatures dropping below 370 degrees, 220 Celsius. Far from the sun, and with little internal heat, its atmosphere radiates away energy until only a faint whisper of weather remains. This is the point in the journey where the solar system feels vast and empty. The worlds are spaced farther apart. the sunlight weakens. Sound, wind, and warmth fade into a soft quiet. Uranus doesn't roar, flash, or storm like the giants closer to the sun. Instead, it lingers like a dream, cool, tilted and drifting through deep space with a kind of slow, elegant solitude. The NASA Voyager team once said, "Uranus is the strangest planet in the solar system." And from here, it's easy to understand why. But the journey does not end with quiet. Just one world farther out, the winds rise again, stronger than anywhere else known. From the quiet sideways world, we head to a place where the winds never sleep, Neptune. At 30 AU, sunlight becomes thin and faint, just 1/900th of what warms Earth. Here, the solar system feels stretched, dark, and distant. And in this twilight frontier, the last of the 8 planets turns slowly in the cold. Neptune, the outermost giant, is an ice giant like Uranus, but darker, richer in color, and far more restless. Its deep blue hue comes from methane in the upper atmosphere, but also from gases and particles we still don't fully understand. Seen from afar, Neptune looks calm, even serene. But up close, the planet is more energetic than any world this far from the Sun has any right to be. This is the home of the fastest winds in the solar system. Storms circle the planet at up to 1,200 miles per hour, nearly twice the speed of a jet plane. No other world produces winds this strong, especially not a world that receives so little sunlight. It is one of Neptune's great paradoxes. The darker it gets, the faster the winds seem to become. Voyager 2, the only spacecraft to visit Neptune, discovered the Great Dark Spot, a swirling storm nearly the size of Earth. Years later, when telescopes looked again, it was gone. New dark spots have since formed in different locations, appearing and disappearing like weather patterns that shift over decades. Beneath Neptune's clouds lies a thick mantle of icy materials. Water, ammonia, and methane squeezed into exotic, high-pressure states. Deeper still, some models suggest carbon could crystallize into diamond rain, falling like glittering stones through the interior. Laboratory experiments support the physics, though the details remain uncertain. A reminder that Neptune still guards its secrets. Its rings are faint, thin, and delicate, shadowy arcs of dust and dark material that circle the planet like subtle brushstrokes. They don't shine the way Saturn's do, but they whisper of collisions, captured fragments, and the quiet shaping of gravity. Orbiting Neptune is one of the solar system's most intriguing moons, Triton. Triton moves in a retrograde orbit, circling Neptune the wrong way, suggesting it wasn't born here. Most likely, Neptune captured it long ago. Perhaps a former dwarf planet from the Kuiper Belt. Its surface is cold and pale, carved by nitrogen frost. But Voyager also saw something unexpected. Geyser-like plumes erupting from beneath the surface, shooting nitrogen gas miles into the sky. Even in this remote place, something underground is warm enough to move. Triton may hold a subsurface ocean of its own, a hidden sea warmed by tidal forces, much like Europa or Enceladus. Here, at the edge of the planetary system, the character of the solar system changes. The giants fade, the sun becomes a distant point, and the worlds beyond Neptune are no longer dominated by gas or rock, but by ice. Neptune marks the end of the planets, but not the end of the solar system. As the Voyager team wrote, Neptune is a dynamic world, full of surprises, and leaving it behind feels like stepping off the map into a region where sunlight barely reaches and where a new kind of landscape begins. Beyond Neptune lies a frozen frontier, the Kuiper Belt. Beyond Neptune, past 30 AU, the solar system changes again. The giants no longer dominate. The sun is now a distant lamp, dim but steady. And ahead spreads a broad, frozen frontier, the Kuiper Belt, a second, colder asteroid belt, stretching from 30 to 55 AU. But unlike the inner asteroid belt, this region is not built of rocky fragments. It is composed mainly of ice, water ice, methane ice, ammonia ice, mixed with rock in smaller amounts. The Kuiper Belt is essentially a freezer left over from the earliest days of the solar system, preserving material that has barely changed in over 4 billion years. Thousands of objects drift here in slow orbits, from small, icy bodies only a few miles wide to worlds large enough to be planets. And at the heart of this story is Pluto. Pluto, once the 9th planet, always a world Pluto, follows an elongated, tilted path around the Sun, taking 248 Earth years to complete a single orbit. Its surface is covered in nitrogen ice, methane ice, and carbon monoxide frost, painted in pale tans and deep reds by sunlight and chemical reactions. In 2015, NASA's New Horizons spacecraft revealed Pluto not as a frozen relic, but as a surprisingly active world. On the western side lies Sputnik Planitia, a vast plain of nitrogen ice so smooth that it has almost no impact craters, meaning the surface is geologically young, reshaped by slow convection like a pot of cold, thick soup. Mountains of water ice, some soaring several kilometers high, rise from the edges of the plain, acting almost like floating icebergs in a sea of softer nitrogen. Hints of a subsurface ocean, still liquid, insulated deep below the crust, have also emerged. Pluto may be far colder than any earthly environment, but cold does not always mean inactive. Pluto's demotion from planet to dwarf planet wasn't because it became less interesting. It was because astronomers discovered many other Pluto-like worlds nearby, meaning Pluto wasn't the oddball. It was simply the first member of a whole new class we hadn't recognized. As Alan Stern, principal investigator of New Horizons, put it, Pluto is the ambassador of a whole new class of worlds. Other dwarf planets, the hidden family beyond Pluto, the Kuiper Belt, holds Haumea, an elongated, fast-spinning world shaped like a football, with a faint ring around it. It holds Makemake, a methane-rich sphere that reflects sunlight with a cold, pinkish glow. And it holds many smaller bodies still waiting to be studied, each carrying the chemical fingerprints of the early solar system. Birthplace of short-period comets. Many comets that revisit the inner solar system every few decades or centuries begin their lives here. Their orbits get nudged by Neptune, by other KBOs, or by slow gravitational resonances, until they fall inward. When sunlight warms their ices, they grow glowing comas and long tails, becoming the comets we see from Earth. Every bright comet with a short orbital cycle may be telling a story that began out here, in this broad, cold ring, where light is weak and the stars feel closer than the sun. The frontier, beyond the planets, crossing into the Kuiper Belt, feels like leaving familiar territory behind. This is no longer the domain of gas giants or rocky planets. This is a realm where ice is the defining material, where worlds drift slowly in deep cold, and where the early solar system sleeps beneath frozen crusts. It is a region of subtle color, slow motion, and long stories. And farther still, some objects wander on wild, stretched-out paths, thrown long ago into unstable orbits that carry them far beyond this quiet belt. But not everything beyond Neptune follows neat circular paths. Some worlds were thrown into wild, stretched-out orbits, into what we call the scattered disk. Beyond the frozen quiet of the Kuiper Belt lies a region where order begins to fracture, where orbits stretch, tilt, and wander, where distance no longer follows a neat pattern, and the solar system starts to look wild. This is the scattered disk, a realm that overlaps the outer Kuiper Belt but extends much farther, populated by objects whose orbits are steep, elongated, and unpredictable. Unlike the Kuiper Belt, where objects follow relatively stable, circular paths, scattered disk objects behave as if they've been kicked outward, tugged into stretched orbits long ago. Most astronomers believe this happened because of Neptune. In the early solar system, when everything was still unsettled, Neptune's gravity swept through the outskirts, nudging some icy bodies outward, pulling others inward, and scattering many into elongated trajectories. Some interactions between large objects themselves may have added to the chaos. Slow gravitational dances that pushed worlds out of their original neighborhoods. The result is a population of icy worlds on orbits so extreme that they spend most of their lives in deep, dark space and only occasionally return toward the sun. Among these scattered worlds, two stand out. Eris. Heavier than Pluto, Eris is a dwarf planet, slightly smaller than Pluto in size but more massive. Its orbit is far more tilted and far more stretched, carrying it well beyond Pluto's range. The discovery of Eris in 2005 reshaped astronomy. It was one of the key triggers that led to the redefinition of the word planet, a change that placed Pluto and several others into the new category of dwarf planets. Eris represents the scattered disk at its most dramatic, a world exiled into a far-reaching orbit by ancient gravitational interactions. Sedna. The longest year. Even stranger is Sedna. Sedna's orbit is so stretched that it takes more than 11,000 years to complete a single lap around the Sun. For comparison, all of recorded human history covers only part of Sedna's most recent year. At its farthest point, Sedna may reach number 937 AU, almost 1,000 times the Earth-Sun distance. It hardly belongs to the Kuiper Belt anymore, yet it is not quite part of the Oort Cloud. Instead, it sits between the two, a clue, a bridge, a reminder that the outer solar system doesn't have rigid borders. Sedna's orbit is also a mystery. No known planets can pull it into such a shape. This has led scientists to propose dramatic possibilities. Perhaps the Sun passed near another star in its youth, tugging Sedna outward. Or perhaps an unseen giant. The hypothesized Planet 9 still lurks far beyond Pluto, shaping the deep architecture of the solar system. Neither idea is confirmed. Both remain open doors. As astronomer Scott Kenyon says, objects like Sedna are fossils of the solar system's early history, frozen records of events no one witnessed, but whose signatures remain carved into their orbits. A dynamical frontier. The scattered disk is the dynamic edge of the solar system, a place shaped by ancient violence, gravitational close encounters, and long, slow migrations. If the Kuiper Belt is a tidy freezer of ancient materials, the scattered disk is the drawer where things were thrown after the solar system's most chaotic years. These worlds wander in the dark for millennia, tracing paths that stretch far beyond the realm of planets. And just past them, the geometry of the solar system changes altogether. Far beyond these wild orbits, the solar system stops being a disk and becomes a sphere, the Oort Cloud. Beyond the scattered, tilted orbits of the scattered disk, the solar system changes shape once more. It stops being a disk. It stops being a plane. It becomes a sphere, a vast frozen shell surrounding everything we know. This is the Oort Cloud, the hypothetical but strongly supported outer reservoir of the solar system, a region so distant that even the word far barely begins to describe it. The inner edge begins around 2000 AU from the Sun. The outer edge may extend to 100,000 AU, or even farther, roughly 1/3 of the way to the nearest star, Proxima Centauri. If the solar system were a city, then Neptune's orbit would be one neighborhood, and the Oort Cloud would be the faint suburban edge you can barely see on a distant horizon. But unlike neighborhoods, this outer shell is nearly empty, except for trillions of small, icy objects, a spherical cemetery of ice. The Oort Cloud is thought to contain frozen remnants of the solar system's earliest years: water ice, methane ice, ammonia ice, dust, and rock, the same raw materials that once built comets and planets. We have never observed an Oort Cloud object directly. They are too small, too dark, and far too distant. Yet the evidence for their existence is overwhelming. Whenever we trace the paths of long-period comets, comets with orbits lasting thousands or even millions of years, we find the same story. Their trajectories point back to a vast spherical swarm far beyond the planets. Their directions are scattered uniformly across the sky, not from a disk, not from a belt, but from a cloud. Jan Oort first pieced this together, and the region now carries his name. Origins: born here, captured. Their most Oort Cloud objects likely began their lives closer to the Sun. During the chaotic early days of the solar system, the giant planets Jupiter, Saturn, Uranus, Neptune scattered countless icy bodies in all directions. Some were ejected completely. Some were captured by the Sun, but flung into immense, elongated orbits. Orbits so wide that they would take millions of years to complete. These became the seeds of the Oort Cloud. But not all of its members were born here. Some may be interstellar immigrants, objects that once orbited other stars, only to be captured by the Sun when it passed through dense star-forming regions in its youth. The idea that pieces of other solar systems now sleep at the galaxy's edge is one of the most intriguing possibilities in modern astronomy. The home of long-period comets, the Oort Cloud is the source of the most spectacular comets you may see from Earth. The ones with huge, graceful tails stretching across the night sky. These comets begin their journey when something disturbs their orbits: a passing star, a shifting tidal force from the Milky Way, or even the slow gravitational ripple of giant molecular clouds. When that happens, a frozen body that has slept for billions of years begins falling inward. It warms. It brightens. it becomes a comet visible from Earth, a messenger from a place far beyond anything our spacecraft have reached. Some comets we've seen in human history may have begun their fall before humans existed, gliding inward from tens of thousands of AU away. The boundary where the sun fades. The farther you go into the Oort Cloud, the weaker the sun's gravity becomes. At 100,000 tart AU, the pull of the sun is no stronger than the pull of passing stars and the subtle tides of the Milky Way itself. If you could stand on an Oort Cloud object, a lonely lump of frozen rock, and look back toward home, the sun would appear as a bright star, a little more luminous than the surrounding constellations, but not by much. Here, you are not just far from home. You are at the place where the solar system blends into the galaxy. Jan Oort once described it simply. The Oort Cloud is the solar system's distant icy reservoir, but the scale makes even that feel small. This is the true outer shell of our sun's family, silent, ancient, and unimaginably vast. And yet, we are still not quite outside, because even here, at the edge of the Oort Cloud, the sun still has influence. Faint, weak, but present. To leave completely, we must cross one last invisible boundary. But even here, in this frozen shell, we are still under the sun's breath. To step truly outside, we have to cross one last invisible border, the heliopause. For billions of miles, everything we've passed, every planet, every moon, every icy remnant, has lived inside one vast invisible structure shaped by the sun. Not a wall, not a shell, but a bubble of charged particles carried outward by the constant flow of the solar wind. This bubble is called the heliosphere, and it is much larger than the planetary system itself. The solar wind rushes outward in all directions, racing faster than the speed of sound through space, until it meets resistance from the thin plasma that fills the space between the stars. At that encounter point, something dramatic happens. Termination shock, where the wind breaks roughly 80 to 100 AU from the sun. Depending on direction, the solar wind suddenly slows from supersonic to subsonic. It is as if the sun's breath hits a soft, invisible wall of interstellar material and begins to compress. This boundary is the termination shock. It is not violent in the way storms are violent, but it marks a sudden change in the very nature of the space around us. Inside this line, the solar wind flows freely. Outside it, the wind becomes sluggish, bent, squeezed, and disturbed. That region between the termination shock and the final boundary is where the heliosphere becomes turbulent. The heliosheath, a stormless turbulence. The heliosheath is a vast, messy buffer zone. Here, the solar wind slows to a crawl, jostled by the galactic environment. Particles collide, flow lines twist, and the sun's influence weakens but does not vanish. It is like approaching the edge of a tide pool, where the water from the sea pushes in, just as the water from the pool pushes out. A place of transition, not conflict. But beyond the heliosheath lies the real boundary. The one that Voyager crossed. The one that separates our star from everything else. Heliopause, the boundary between two realms. The heliopause is where the outward pressure of the solar wind becomes equal to the pressure of the interstellar plasma. Inside this boundary, nearly all charged particles come from the sun. Outside it, they come from the galaxy. from supernovae, dying stars, and the magnetic tides of the Milky Way. It is a subtle border, a membrane, not a wall, a place where the identity of space itself changes. Crossing it means leaving the sun's neighborhood. The heliopause is where our sun's influence ends and the galaxy's influence begins, said Ed Stone, the legendary Voyager project scientist. And the shape of this boundary is still debated. Some models show it stretched like a teardrop, blown back by our motion through the Milky Way. Others suggest it is closer to spherical, nudged and sculpted by shifting interstellar fields. Whatever its shape, the meaning is the same. Past the heliopause, the sun is no longer the dominant sculptor of space, a soft doorway into the galaxy. Reaching this place is not the end of the solar system. The Oort Cloud extends far beyond, but it is the end of the sun's environment. This is the point where the solar system's weather stops and the galaxy's begins. If you stood on a tiny chunk of ice here and looked back toward home, the sun would still shine, but only as a bright star among other stars. And floating somewhere in this quiet boundary region are two small machines, nearly 50 years old, still moving outward. Voyager 1 and Voyager 2, the farthest travelers humanity has ever sent, are already on the other side of this invisible gateway. In 1977, long before many of us were born, humanity threw two small machines into the sky, not as weapons, not as tools, but as messages. Voyager 1 and Voyager 2 were launched only weeks apart, timed perfectly for a once every 176-year alignment of the outer planets. NASA called it the Grand Tour, a gravitational highway that would let a spacecraft visit multiple giants with minimal fuel. No one then imagined that these machines would become the farthest travelers in the history of our species. The Grand Tour, a journey. No human could make Voyager 1, swept past Jupiter in 1979, then Saturn in 1980, capturing the first close images of their clouds, rings, and moons. After Saturn, it was directed upward, out of the plane of the solar system, toward interstellar space. Voyager 2 took the more ambitious path. Jupiter in 1979, Saturn in 1981, Uranus in 1986, Neptune in 1989, the only spacecraft ever to complete the full Grand Tour. From the stormy poles of Jupiter to the blue methane winds of Neptune, the Voyagers revealed landscapes no one had ever seen. Through their eyes, the solar system became a real place, not just drawings in textbooks, where they are now. Farther than any human dream. Today, Voyager 1 is more than 15 billion miles from Earth, over 160 AU away. Its radio signal, traveling at the speed of light, takes over 22 hours to reach us. Voyager 2 is farther than 130 AU, slower but still moving at nearly 15 km/h through the dark. Both spacecraft have passed the heliopause, Voyager 1 in 2012, Voyager 2 in 2018, making them the only human-made objects in interstellar space. They are still talking to us. Faint whispers, faint enough that a single photon in billions must be captured by antennas the size of football stadiums. Their aging hearts, running low, but still beating. Each Voyager is powered by a radioisotope thermoelectric generator, a slowly cooling block of plutonium. Every year the power drops, and NASA must choose what to turn off. First the heaters, then the cameras, then the instruments one by one. Inside each spacecraft, The flight computer, built in the 1970s with memory smaller than a photo on your phone, still runs code written decades ago, still correcting course, still keeping time. By the late 2020s or early 2030s, the Voyagers may fall silent, but silence doesn't mean the journey ends. The golden records, bottles cast into the cosmic ocean. Bolted to the side of each spacecraft is a 12-inch golden disc, an archive of who we were when we first reached for the stars. Sounds of Earth, rain, wind, birds, a heartbeat, music from Bach and Beethoven, Chuck Berry's Johnny B. Goode, blues from Blind Willie Johnson, greetings in 55 languages, drawings of our DNA, the shape of a human hand, a map pointing to our sun using the rhythm of distant pulsars. If someone or something ever finds them, they will hear us. Carl Sagan called them messages in a bottle thrown into a cosmic ocean. Their future, time beyond our imagination. In a few years, the Voyagers will stop sending data, but their paths will remain unchanged. In 40,000 years, Voyager 1 will pass within 1.6 light-years of a small star, Gliese 445. Voyager 2 may come close to Sirius thousands of years after that. And in millions of years, long after every city and nation on Earth has vanished, long after mountains rise and fall, these two little machines will still be drifting between the stars. Ed Stone once said, "The Voyagers will be the longest-lived objects humans ever made." A human moment at the edge of the Sun Voyager has traveled more than 160 AU. But to reach 1 light-year, it would need to go another 63,240 AU. In other words, after nearly 50 years of flight, it has just stepped off the shore. The night is still young, the ocean is still vast, and our two messengers are only beginning their silent journey. They are in the stars now, Carl Sagan said simply, and somewhere in that deep, quiet darkness, the golden records spin slowly, carrying the fingerprints of a world they will never return to. When the Voyagers crossed the heliopause, they didn't hit a wall. There was no shock, no jolt, no moment that felt like stepping off a cliff. The change was softer, like walking from warm air into cool air, invisible, but real. They had entered the interstellar medium, the thin ocean that fills the space between stars. Not empty, just unbelievably thin. We often imagine interstellar space as a perfect vacuum, but it isn't. Every cubic centimeter out here holds a few atoms, mostly hydrogen and helium, just a handful of particles in a volume the size of a sugar cube. It sounds like nothing. But over light years, those few atoms shape entire regions of the galaxy. Compared to the inside of the heliosphere, where the solar wind packs thousands of particles into each cubic centimeter, the interstellar medium feels like a different universe. And for the Voyagers, every instrument confirmed it. The particle density changed. The magnetic field changed. The texture of space itself changed. Dust, gas, and the leftovers of dead stars floating through this thin ocean is the stuff of creation. Tiny grains of carbon and silicate dust. Cold hydrogen clouds. Charged particles blown out by ancient supernovae. Wisps of plasma shaped by galactic magnetic fields. Every atom of iron in your blood, every bit of calcium in your bones, was once forged inside a star, cast into this medium, and recycled into new worlds. The interstellar medium is quiet, but not dead. It is where stars begin, the shock waves that build the future. When a massive star explodes, the shock wave travels for light years, sweeping and compressing this thin material. If the compression is strong enough, gravity takes over. A cloud collapses, a knot thickens, temperatures rise, and a new star ignites. Around it, a disk forms. Planets take shape, oceans appear, and maybe, eventually, something looks up and asks where it came from. This cycle, stars dying to create new stars, is how galaxies stay alive. Interstellar space isn't empty. It's the raw material for everything that ever was, and everything that will be. A different kind of wind. Inside the heliosphere, we lived under the steady pressure of the solar wind. Out here, that wind is gone. In its place is the faint push of winds from other stars, and the subtle pull of the galactic magnetic field. A field so vast that it shapes the boundaries of entire star systems. The Voyagers don't feel it the way we feel wind on Earth. They only detect numbers, changes, patterns. But the story is clear. They are no longer in the sun's domain. A tiny step into a very large ocean, Alpha Centauri, the nearest star, is still 424 light-years away. That's $268,000 AU. Voyager 1 has traveled barely 160 AU, a fraction of a fraction, just 0.06% of the distance. And yet, this is the farthest we've ever gone. From here, from this quiet drift in the interstellar medium, let's look back. All the distances we crossed, all the worlds we passed, now shrink into a single simple truth. Our entire solar system is just a tiny clearing inside a far bigger forest. Zoom out, and the planets vanish. Zoom out further, and even the Oort Cloud becomes a faint haze around a dim star. The sun, our sun, lives in a small suburb of the Milky Way, tucked gently into the Orion Arm. Around us, 100 to 400 billion stars burn, drift, and circle the galactic center. And we orbit that center at 220 kilometers per second, completing only one lap every 230 million years. We are always moving, always circling, always drifting. And yet, to us, everything feels perfectly still. That's the comfort of living inside a stable system. Our nearest neighbor, still impossibly far. The nearest star system, Alpha Centauri, is 4.24 light-years away, about 268,000 AU. Voyager 1, our most distant messenger, has traveled only a few hundred AU, a single step, on a path that would take tens of thousands of years. And yet, we made that step. And tonight, you followed it farther than any spacecraft will go in your lifetime. A universe that is large, but gentle. The scale may feel overwhelming, but scale is not danger. There is no catastrophe waiting in the dark, no hidden threat drifting toward us. Our solar system is stable. Our star is calm. The planets follow their paths with patient precision. Every morning, the sun rises exactly as it did yesterday. And every night, its warmth continues to protect this small world we call home. In all this vastness, you are safe. A soft philosophy to close the journey. Being small does not make us insignificant. It makes the universe feel peaceful. It reminds us that we do not have to hold everything. We do not have to understand everything. The cosmos moves whether we worry or not. And tonight, it will keep moving, gently, quietly, without needing anything from you. Above you is a quiet star. Beneath you is a small, warm world. And far away, the Voyagers drift, carrying a message from all of us into the dark. You can let go now. Let the universe keep watch. The universe will keep moving. And tonight, you can rest.